They won't throw anything this. I've had a word with them before.
Thank you very much, and good evening, Knutsford. Do the lights go down slightly? Yep. So yes, this is the end of everything. The wonderful introduction tells you all you need to know. So an alternative way of thinking of this particular talk is to think of it from the Disney perspective. We're going to eternity and beyond. So what I'll be doing is giving you a little bit of a prologue and then talking about the future of the Earth, the Sun and the solar system. Then we'll be looking a little further into the future, into the far future of what's going to happen to stars and galaxies. And then we're going to be looking into the far, 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 far future and the ultimate fate of the universe. And then I'll just finish with a little bit of an epilogue. So yes, as you've been warned, this is the second part of a double act. The beginning of everything. So that was a couple of years ago or so. And I'm not going to recap everything other than to say that in the beginning of everything, the universe started off as a tiny little thing, the observable universe, which is currently 100 billion light years across. Everything used to be a lot closer together, basically just separated by a few centimeters. The universe expanded, and within the first 3 minutes, the universe made all of the protons and all of the neutrons that produced all of the hydrogen and the helium that ultimately got processed into everything we see in the universe today. In other words, stars have been fusing hydrogen into helium, helium into carbon, nitrogen, oxygen, and ultimately you. So we are going to take it on a timeline here to keep you on track, or to keep me on track, to give you a guide as to where we're at. I'm going to run a timeline across the top of every slide. So if these numbers refer not to years into the future, but 10 to the power something years into the future. Each small box means 10 years further into the future than the previous box. And what I'm going to do is run a red box along from left to right so that we can keep track of where we are. In other words, 10 to the power 2, 100 years, 10 to the power 3, 1,000 years into the future. And then we're going to go 4, 5, 6, 1 million years into the future, 7, 8, 9, 1 billion years into the future, 10, 11, 12, 1 trillion years into the future. So to start with, we'll occasionally be using millions and billions, but eventually these numbers start getting so big, we'll just rely on the 10 to the power number to remind ourselves how far into the future we are looking. And I'm not going to cover topic by topic. I'm going to try and keep everything in time order. And I'm grateful to the work of Adams and Laughlin, who produced a paper some years ago in which they tried to calculate when, or at least likelihood of when, particular astrophysical events are likely to occur in the future. And I've tried to keep my slides in strict chronological order, even though the subject matter might be jumping around a little bit. So we're not going to start 10 years or 100 years into the future, because nothing, astronomically speaking, interesting is going to happen. Let's assume we don't blow ourselves up in nuclear war. Let's assume we get climate change under control. One thing that we are fairly sure of is that the Earth has been slowing down for quite a while. It's varying a little bit in the short term, but we're fairly sure that the Moon is slowing down the Earth, and in 1,000 years or so, instead of adding a leap second every few years, which is currently what we do because of the slowdown of the Earth, in 1,000 years or so, we'll probably have to add leap seconds into our clocks every few weeks rather than every few years. That's something that we can predict. There are various other things that we can't really predict with any sort of certainty. We know that some stars are going to go supernova, but it's almost impossible to predict when. But we do know, for instance, that we're going to get a new pole star in about 10 to the 4 years. In another 10 to 20,000 years, we're going to get a new pole star. The precession of the Earth's axis, points to a particular point in space, which is slowly varying and drawing out this large circle on a timescale of 26,000 years or so for the full cycle. That means that the direction in which the Earth axis points traces out a big circle on the sky. At the moment, the Earth's axis is pointing towards Polaris on the right-hand side there. But in another 10,000 years or so, when it's gone halfway around this circle, it'll be pointing close to Vega. So a lot of people currently believe that the Polaris, the pole star, is the brightest star in the sky. I don't know where this myth comes from, but in another 12,000 years, they'll probably be right, because Vega will be very easy to spot, and that will be almost the pole. So apart from making this really easy for Boy Scouts to point out which way is north, what's the consequence of the pole star changing? Well, at the moment, the Earth's axis is such that when we think about the Earth's orbit around the sun being an ellipse, we're closer to the sun during northern winter, which tends to offset slightly the fact that summers are warmer than winters. But when the Earth's axis, instead of pointing at Polaris, when the Earth's axis is pointing in the other direction towards Vega, that means we're going to be closest to the sun because of the elliptical orbit during northern summer rather than during northern winter, which means the seasons are going to be just a little bit more exaggerated. And this is a common theme for what's going to come in years to come. The fact that the Earth's climate, regardless of what we do in terms of man-made contributions to carbon and CO2, there will be changes to the Earth's climate because of the changes to the Earth's spin and the Earth's orbit. These variations in climate, due to various aspects of the way the Earth moves, are called Milankovitch cycles. I'm going to mention those but not say an awful lot about them. You can go and look them up if you want to know more about these things. On a slightly longer time scale, we're now going somewhere between 10 and 100,000 years into the future. The Voyager space probes are going to be passing the nearest stars. They're leaving the solar system, but even though they have gone way past Pluto, there's still a long time before they get to the nearest star. So the Voyager probes were launched in the 70s, 1977, a few weeks apart, heading off towards Jupiter, Saturn, and Jupiter, Saturn, Uranus, and Neptune in the case of Voyager 2. Now they're heading out of the solar system, and Voyager 1 at the top there is going to be heading off such that in another somewhere between 10 and 100,000 years, somewhere around about 40,000 years or so, it's going to pass a star called Gliese 445. If there's any intelligence in that particular solar system, they might pick up Voyager. More likely, it's going to go straight through that solar system, in one side, out the other side, and carry on its journey. Similarly for Voyager 2 down the bottom here, that's going to pass very close to the star Ross 248. It doesn't seem very likely that there's any intelligence around that particular solar system, but it will go straight through that solar system and carry on through the galaxy. The Pioneers are also on this diagram. The Pioneer space probes were launched in the early 70s rather than the late 70s, but they were traveling more slowly, so they haven't actually got as far as the Voyager space probes. On the right-hand side there, Pioneer 10 is heading off in the direction of Aldebaran, and Pioneer 11 on the left here is heading off in the direction of the center of the galaxy. So it might well be that they pass through definitely solar systems, maybe intelligent life, within 10 to 100,000 years. On a similar timescale, the Earth is going to be changing. We know from the historical records that ice ages have come and gone. We've had periods of ice ages, and we've had periods called interglacials, the warm periods in between ice ages. These come and go on timescales of order 100,000 years or so. And we know from the historical record that the Earth entered an interglacial warm period relatively recently, which means we're due for an ice age, roughly speaking, in 100 or so thousand years' time. And this reason for the ice ages coming and going is another aspect of Milankovitch cycles, another change to the Earth's orbit. Now, we're still on 10 to the 5, so we're still something like 100,000 years into the future. All of this time, the moon has been slowing down the Earth. The moon is tugging on the ocean tides that it generates, and that slows the Earth down. And remember, leap seconds are currently introduced every few years. We said after 1,000 years, they'd need to be introduced every few weeks. After 100,000 years, leap seconds would need to be introduced something like every day. In other words, the length of the day wouldn't be 24 hours. At this particular point, 100,000 years into the future, the length of the day is roughly 24 hours and a second. So we would need to keep adding leap seconds continuously every day of every year. sometime or another, we're going to have to sort out what we do about leap seconds. Do we keep putting them into the clocks, or do we stop putting them in? So after 100,000 years, if we do keep using them, we'll have to put them in every day. We don't know when stars are going to go supernova, but for instance, Eta Carina, from this astronomy picture of the day from a few years back, Eta Carina has been blowing off the outer part of its atmosphere for quite a few years now. In other words, it's been sloughing off its outer atmosphere, and it looks like it's generating a sort of prototype planetary nebula almost of gas around it. It looks like this is a prime candidate for a star to go supernova, and it is widely thought that it will go supernova within the next 100,000 years. We can't be precise. We can't tell if it's going to go off in 1,000 years or 100,000 years or maybe a little bit more. But this is the sort of timescale that we can expect Eta Carina to go supernova. Similar timescales apply for Betelgeuse. That looks like a bit of a fake image. Well, it sort of is, other than the fact that the starscape is a photograph of the stars behind this particular observatory, which is in Prague. But the person who took this particular nightscape photo has artificially enhanced the brightness of Betelgeuse to show what Orion would look like. Perhaps you recognize Orion there with the belt, etc. And there obviously is the position of Betelgeuse. This is what Orion might look like when Betelgeuse decides to go off. It'll completely ruin that constellation. Maybe it's worth it for the spectacle of having a bright light in the night sky and probably visible during the day as well. But it will ruin the constellation, let's face it. But as well as stars going supernova, there are other things that could potentially be a problem. Betelgeuse is hundreds of light years away, which sounds like, well, that's far enough that if it decides to explode, that's not much of a problem. But there are some stars, even though they are thousands of light years away, that could still be a problem. So for instance, a Wolf-Rayet star, this Wolf-Rayet 104, these are rather unstable stars that seem to have a great deal of matter circulating around them. This particular star, although it's 7,000 light years away, when it does decide to die, whenever that might be, perhaps on a time scale of 10 to the 5 years, it could produce a radiation burst even more powerful than a supernova. These sorts of stars, often with very fast circulation, produce jets via a mechanism that we don't fully understand, much like the jets produced by supermassive black holes. If that jet happens to be pointing towards Earth, the rotation produces these jets, and we think we know which direction the jets are pointing, but we can't be sure. If we happen to be lined up with one of those jets when this star dies, a huge amount of radiation is going to come out in the direction of these jets. Now, we don't think these jets are pointing directly at Earth. We think they're pointing a few degrees off, and therefore the radiation produced by the death of this star will probably miss us. If we're really unlucky and that jet is pointing in our direction, even at a distance of 7,000 light years, in principle, the radiation from one of these objects could kill basically all life on Earth. That gives you an idea of just how energetic these so-called gamma ray bursts can be, these deaths of stars that generate huge amounts of radiation in very specific directions. These GRBs can be seen from enormous distances, even in other galaxies, and therefore something that's only 7,000 light years away is virtually on our doorstep. It's something we need to be aware of. Our sun and all the other stars in the Milky Way are orbiting around the center of the Milky Way. It takes hundreds of millions of years to do an orbit or so. But it's been calculated that in 1 million years or so, although all the stars are doing completely independent orbits around the Milky Way, it just so happens we're going to come close to one other. It's not necessarily gravitationally bound or being pulled by us. It just so happens that we're orbiting around the Milky Way, and one other star is going to happen to come close and then drift away again. This star is called Gliese 710, and it's going to come close to our solar system and then move away again. But notice that at its closest, it actually comes closer than the rest of the Oort cloud, which means that the Oort cloud, being a few trillion pieces of bodies of various rock and ice, it is probable that as Gliese comes close to us, Gliese 710 comes close to us, it'll disturb a lot of the elements in the Oort cloud, and some of them are going to come thundering into the inner solar system. It's been predicted that when this happens in 1 million years or so, it is probable that we'll end up with naked eye comets, probably one a month, for the next 1 million years or so. So in other words, there's plenty of material here to be perturbed by Gliese. Some might not come in our direction, but just the ones that do come in our direction will be millions of comets heading in our direction. And it's interesting to note that for a little while at least, our solar system will actually have 2 suns in it. And we know that happens elsewhere. We've all seen it. We know that 2 suns is not that unusual. And so it's interesting to note that we have been alone in terms of the sun has been on its own for billions of years, but in a little while there will be 2 of them. On the same timescale of 1 million years or so, this is not trying to indicate that an impact such as Meteor Crater Arizona happens once every 1 million years. This picture is there for 2 reasons. One, so that we can note, wow, wasn't it lucky it just missed the visitor center. I mean, it only had to be 100 meters over and it would have completely smashed it. But no, the 1 million years is not how often we get a crater like that. The 1 million years is to remind us that on the Earth, weathering systems will remove evidence of old craters. So craters like this that are more than a few million years old, we would never actually notice because they've been weathered. The wind and the rain, etc., would have removed them completely, and so we would not actually know they existed. And you might say, well, yes, that's fairly obvious on something like the Earth, where there's lots of weathering, then we can expect rocks to change over hundreds of thousands or millions of years, but that wouldn't be true of somewhere else. Like, for instance, the footprints on the moon will last forever, won't they? No, they won't, because although there's no weathering as such, there is impact from micrometeorites. So the footprints of Buzz Aldrin there will not last forever. The moon is being pummeled by micrometeorites all the time, and after 1 million years it'll be such that effectively the regolith, the lunar surface, will be completely rearranged by all of these impacts. It's been predicted that even the hardware, even the lunar module descent engine, even the lunar rovers will eventually disintegrate under the impact of micrometeorite bombardment if you simply wait for long enough. So we tend to think of weathering as needing an atmosphere, but if you include micrometeorites, then no, anybody in the solar system can undergo erosion. We're now moving 10 times further into the future, 10 to the 7, 10 million years into the future. We've just said that Voyager and Pioneer, etc., would meet another solar system within somewhere between 10 and 100,000 years. So after 10 million years, Pioneer, for instance, would have already passed through lots and lots of solar systems, assuming it was never caught by an alien civilization who picked it up and thought, what's it we've got here? It will have passed through 1,000 different solar systems. So what's the 10 to the 7 significant for? Well, the plaque that's on the side of Pioneer 10, which basically says this is who we are compared to Pioneer, that's where we came from, a pulsar map saying this is where pulsars are and this is their timing. So if you know about pulsars, you can work out where the Earth is, and we came from the third rock from the sun. So it's a map basically telling you the origin of this particular spacecraft. But after 10 to the 7 years, this is only a piece of aluminium. It's gold coated, but it's essentially just a piece of aluminium. And if you think of space as empty, you must remember that after 10 million years of plowing through the interstellar medium, you will have picked up lots of micrometeorite impacts, dust grains, etc., will have completely pitted and eroded a plaque like that. So after 10 to the 7 years, somebody might conceivably pick up Pioneer 10 and say, that's interesting, it looks like it's artificial as opposed to a natural object, but they would not be able to read the plaque. So if it's not caught in the first 1,000 solar systems that it goes through, if it is caught after that, the people who catch it won't really know where it came from. Now another factor of 10. We're now talking 100 million years into the future, and we're talking about Saturn's rings. But before we talk about the future, it's probably worth asking ourselves, how did Saturn's rings come to exist in the first place? One theory is that a moon like Mimas was disintegrated, perhaps with collision with a comet or something like that, and the debris formed the rings, and some of the debris reformed a moon like Mimas. I mean, let's face it, when you look at a moon like that, you might think to yourself,
that's no moon, it's a space station.
It does indeed bear a canny resemblance to the Death Star. But it is thought that if you do a simulation of how the rings might have been produced by a moon, so for instance, you take a small moon, you pulverize it, let's imagine it gets hit by another moon or a comet or something like that. If you pulverize a moon with about the mass of Mimas, what is going to happen to the debris? And a simulation carried out by these people here, credited on the side, shows you what happens to the debris. Notice the time scale in the bottom right. It only takes hours or days to actually form a ring system. It's surprising that if you pulverize a moon, it doesn't all stay in one cloud for years and years and years. It gets spread into a ring system relatively quickly. And it's thought that that happened millions of years ago. Why millions of years ago? Because the debris slowly migrates inwards. The individual particles do interact with each other, and they don't stay in orbit around Saturn forever. They gradually migrate. In effect, each particle in Saturn's rings is slowly spiraling inwards, and eventually will rain down on the surface of the planet itself. That's been happening, we believe, for millions of years, and therefore, when we project 10 to the 8, 100 million years into the future, we think all of these particles will have migrated and rained down on Saturn, and the rings will be no more. So make the most next time you see Saturn, and remind yourself they haven't been there forever, and they won't be there forever. Okay, millions of years, but basically, they won't be there forever, and eventually there will come a time when people don't get the majestic sight of Saturn's rings. The other thing we should remember on a similar timescale of 10 to the 8, 100 million years or so, we tend to think of the solar system as being clockwork, especially those of us who build orreries and say, isn't it wonderful how the solar system behaves like Newtonian clockwork, whether we build an orrery or a tellurian, which shows us the motion of the Earth and moon around the sun. There's the temptation to think that's the way the solar system is. It's clockwork. But we have to remind ourselves that on these timescales of 100 million years or so, we cannot predict where anything is going to be. If we currently look at where Jupiter is and how fast Jupiter is moving, we can calculate where Jupiter is going to be next year, or in 100 years, or in 1,000 years, or 10,000 years, but we can't push that to 100 million years. The solar system is chaotic on this timescale. We don't even know if Jupiter will still be here in 100 million years. It could be that Jupiter would have flung other planets out of the solar system. It could be that chaotic interactions between the planets result in a completely different solar system than the one we see today. So orreries are good for thousands of years. You can certainly use your app on your phone or an orrery and say, that's where the planets are. Where were they, for instance, 2,000 years ago? Could that have been the Star of Bethlehem? 2,000 years? No problem. 100 million years? No chance. It's completely chaotic on that sort of time scale. Still on 10 to the 8 years, still on 100 million years into the future. We currently sit about here. The sun, in terms of where we sit in the Milky Way galaxy, we are currently sitting in between two spiral arms, which means we're in a relatively low density part of the Milky Way. We haven't got that many neighbors. Yes, our nearest stellar neighbor is 4 light years away, and obviously there's ones beyond that. But if we work out how many stars are there within 100 light years or so, there are not many compared to the number of stars that we would have as neighbors if we were in a spiral arm of the Milky Way. And the Milky Way rotates, roughly speaking, once every 100 million years or so, maybe a couple of 100 million years. And what's going to happen is, as the Milky Way rotates, we are going to end up in one of these spiral arms. The spiral arms are not fixed, they are just regions of high density. And we are going to end up in one of those regions of high density in something like 100 million years or so. So what difference does that make if we happen to be in a spiral arm versus not in a spiral arm, in between two spiral arms. What difference does it make? Well, the difference it makes is that we will have many more stellar neighbors. In other words, we'll have lots of stars around us, and those stars will, generally speaking, be quite close, not necessarily 4 light years or 6 light years or 8 light years away. So what are the consequences of having lots of stellar neighbors? Well, one of the consequences we can see in the fossil record. If you look at how many species have ever gone extinct as a function of time, this is the last 500 million years or so, we see the number of extinctions tends to spike, and we get a number of high-level extinctions, a number of them, it looks like quite a few of them, over a time period of a few 100 million years. So very roughly speaking, every 100 million years or so, we seem to have a spike and a whole load of species go extinct. The last one on the right-hand side there, the KT, the boundary between the Cretaceous and the Tertiary phase was the death of the dinosaurs there. So what's going to happen when we go into a crowded part of the Milky Way is we are going to find lots of stellar neighbors. Just like Gliese 710 is going to disturb the Oort cloud and send comets our way, the same will happen. When we've got lots of stellar neighbors, we are much more likely to have a local star perturb all of the rocks in our neighborhood and send loads of asteroids and comets our way, some of which are going to impact the Earth. This is, of course, an artist's impression of a very large lump of rock, apparently headed towards Italy. Okay, bad news for Italy, but of course, if it's a big lump of rock, it's going to be bad news for the entire planet. When we're talking about extinction level events, what we mean is species will be exterminated. It's not going to be a meteor crater which makes a little bit of a dent in Arizona. This is going to affect the entire planet, and species will die. The question is, will one of those species be us? It's very difficult to predict. We hope it won't. We hope we will have learnt enough to deal with the situation, either by sending Bruce Willis up to avoid this particular incoming asteroid or finding some other way of surviving an impact from a large lump of rock. But another consequence of having lots of neighbors producing lots of impacts on Earth, if we have lots of neighbors, then one of those neighbors might conceivably go supernova. At the moment, we haven't got any candidates close to us. The nearest star that looks like it might go supernova is hundreds of light years away. But if we have many more neighbors, then perhaps one of those neighbors could be a red giant on the verge of going into a supernova phase. Now, we know it's going to be a problem if a supernova goes off within 100 light years or so. 600 light years, Betelgeuse, probably okay. If a supernova goes off within 100 light years, that could be a danger to us. If a supernova goes off within 20 light years, it's been calculated that that could sterilize the entire planet. So we definitely don't want that to happen. There's probably not much we can do about, but the point is, if we're in a spiral arm, we're going to have more neighbors, it's more likely to happen. And we know that supernovae have gone off in the past. We know that some new supernovae have gone off not that far away from Earth. How can we tell? Because supernovae within 100 light years of Earth produce a particular isotope called iron 60, and that ends up in the sediments of Earth. We can separate that out from other isotopes, and iron 60 generated in supernova is radioactive, which means it doesn't hang around for that long. It's got a half-life of some few million years, and 2.6 million years it says here. So after something of order a few million years, a lot of that iron will have changed into cobalt and eventually into nickel, which means if we look in Earth sediments and we find iron 60, it can't have been there for billions of years because radioactive decay would have changed it into something else. So if we see iron 60 in sediments on Earth, it must have arrived relatively recently, i.e. millions or hundreds of millions of years ago. They haven't been around. Those isotopes have not been around since the birth of the Earth. So stars have gone supernova and have dumped iron 60 in our sediments in the past. So we know it's happened in the past. It could happen certainly in the future. 10 to the 8 years, we're still on 100 million years into the future. the moon is continuing to tug on the Earth. It has been doing for the last 100 million years or so. And it's stealing the Earth's angular momentum. It's slowing down the Earth, so the Earth's spin is slowing down, and as a consequence, the moon now has a larger angular momentum. It's moved further away from the Earth. The length of the day has increased from 24 hours to 25 hours. Leap seconds have gone out the window completely. There's nothing we can do about trying to keep our clocks synchronized. The best we can do is change our clocks from a 24-hour clock system and decimalize it to a 25-hour or a 100-hour system. As a consequence of the Earth slowing down, the moon is getting further away. The total angular momentum of the system is unchanged. So if Earth loses some angular momentum, the moon gains it and moves further away from the Earth. And it won't be too long, after 10 to the 8 years of this happening, it won't be too long, somewhere around 10 to the 9 years or so, before the moon will be too far away for a total eclipse of the sun. In other words, the disk of the moon will be so far away, it won't be large enough to cover the disk of the sun. There will be slight changes to the Earth-Sun distance, but that will still be true. There will come a time when total solar eclipses cannot happen. So for those of you who are eclipse chasers, get in now before 10 to the 9 years. It'll still be possible to have annular eclipses like the one indicated in this astronomy picture of the day, where the disk of the moon is not large enough to cover the disk of the sun. That will continue, and there will be annular eclipses forever, for as long as the moon exists. But total eclipses where the moon covers the sun will not happen after 1 billion years or so. But apart from the fact that we don't get good views of solar eclipses, there's another consequence of the moon moving further away from the Earth on this timescale of 1 billion years or so. The moon has a stabilizing influence on the axis of the Earth. The tilt of the Earth's axis is about 23.5 degrees and has been for an awfully long time. Basically, as long as records show, it looks like the Earth's axis has been about 23.5 degrees. It's never varied by more than about a degree from that particular value. So in other words, this cartoon on the left shows you the variation from, let's say, 22.5 to 24.5 degrees. It hardly changes at all. And remember, it's the tilt of the Earth that determines the seasons and the severity of the summers versus the winters. But if the moon moves further away from the Earth, it will no longer stabilize the Earth's axis. So for instance, if the moon ends up 25% further away, which it will do on this sort of timescale, then the Earth's axis will no longer be affected and stabilized by the existence of the moon, and the Earth's axis can then erratically go all over the place. It could change dramatically to the point where the axis could suddenly go vertical or suddenly go horizontal or change backwards and forwards. We forget the fact sometimes that the moon is stabilizing the Earth's axis and keeping it at 23.5 degrees. So on this sort of timescale, the Earth's climate could go absolutely wild because the Earth's axis will no longer give us spring, summer, autumn, and winter once the axis starts moving all over the place. We're now on a timescale of about 1 billion years, but remember we said Voyager was leaving the solar system on 10 to the 4 to 10 to the 5 years, like Pioneer. It might take 10 to 100,000 years to reach the next solar system. So why have we got Voyager here at 10 to the 9? If it takes 10,000 years to get to the next solar system, it will have passed tens or hundreds of solar systems by the time we get to 1 billion years. But it's thought that the gold disk that Voyager carries will be good for 1 billion years. A bit difficult to calculate, but if you take this particular system, it's a copper disk coated in gold, and we think that is about as stable as you can get. And we think that this disk will still be readable. It's a phonograph, effectively, with audio and video signals embedded in it. We think that will still be playable 1 billion years into the future. And again, if Voyager doesn't get caught by the next 10 or 100,000 solar systems, then it will still, in principle, be readable even 1 billion years later. Why is this disk different to the Pioneer disk, which would be pitted and eroded after only a few million years or so? The difference is this gold disc is protected underneath a cover, and that cover is a piece of aluminium coated in uranium. It's coated in uranium because that has a particular half-life, so anybody picking this up who knows about uranium will be able to figure out how old this particular probe is. But the catch is, after 10 to the 9 years, the disc is fine, but the cover will be so pitted, the instructions are on the cover. So you won't be able to read the instructions as to how to read the disc, unless they know exactly what a phonograph is. How many 15-year-olds know what a record is or a phonograph is? So the idea of you need a stylus and you turn the record at this speed and then you get sounds and video out, it's a shame that the disc will survive but the instructions won't. But okay, let's just hope that Voyager does get picked up in the first 100,000 solar systems that it goes through. If it gets picked up in the first few dozen, it doesn't matter that the disk would ultimately corrode after 1 billion years or so. So we're 1 billion years into the future, and things are going to change, regardless of space probes that we sent out. So the sun is not yet a red giant, but it will be moving towards the red giant phase after a few billion years. We think the sun has got 4, 5, 6 billion years of life ahead of it, but after a few billion years, it is going to start to increase its luminosity. The luminosity is going to go up by perhaps 10% every billion years or so. It's very slow, but on these timescales, it's going to make a difference. It's going to push the Earth into a greenhouse effect. And the surface temperature of the Earth is, before long, going to be about 80 Celsius or so. The oceans will boil, and we're going to have to figure out what we do. Are we going to leave the planet, or are we going to go underground? Can we figure out a way of stopping this happening? It's not obvious how we would possibly do that. The sun, as it goes towards its red giant phase, is going to expand. And it's been calculated that the size of the sun is going to end up comparable in diameter to about the Earth's orbit. So we think to ourselves, okay, this could be a problem. If the surface of the sun ends up getting close to or engulfing the Earth, then it's difficult to see how we can survive that. But the Earth won't necessarily be engulfed by the sun. It is true that if you do the calculation, when you work out how big we expect the sun to be, based on its mass, based on looking at other red giants, we would expect it to be larger than the Earth's orbit. But one thing that is often forgotten is that as the sun expands in the red giant phase, it will have very strong solar winds, and it will lose mass because mass will literally be leaving the surface of the sun, and so the sun will be losing mass. If the sun loses mass, that means the Earth's orbit will be larger because the sun's gravitational pull will not be as strong. And we can see that in this little cartoon. As the sun grows in size, the Earth will actually move away from the sun. So yes, the sun will end up large enough to completely engulf the Earth's orbit. But the Earth might not be there anymore. The Earth might have moved out. It's debatable because there are other effects which some people say, yeah, but maybe the Earth won't move out as far as we would like. But certainly the sun will engulf the old Earth orbit, and it might be that the new Earth orbit is large enough to actually keep the Earth from being engulfed. So it'll definitely get rather on the toasty side, but it won't necessarily completely destroy the Earth. The Earth might survive. What's going to happen after the sun has gone through its red giant phase? It goes to a red giant, it sloughs off its outer layers into a planetary nebula, and the core of the sun ends up as what we call a white dwarf. The sun will already have fused hydrogen into helium and helium into carbon, and what we're left with is essentially a lump of carbon. So we're not sure exactly what that's going to look like. A white dwarf will be about the size of the Earth. It'll be thousands of kilometers across, not millions of kilometers, and it will be mainly made of carbon. Some people have hypothesized that if the pressure is high enough inside a white dwarf, that carbon might actually be in the form of diamond. So it might end up as a diamond 10,000 kilometers in diameter. Who knows? If the sun ends up as a white dwarf, what's going to happen to the Earth? Well, if the Earth survives, a lot of these next slides are going to be if the Earth survives, then we are going to lose our magnetic field. The magnetic field of the Earth is produced by the core of the Earth being molten. The heat at the center of the Earth is nothing to do with heat coming from the sun. The reason the core of the Earth is molten is because of radioactive decay of elements that have been around for billions of years. But eventually those elements are going to cool down the core of the Earth because essentially the radioactivity will eventually die out on timescales of many billions of years. So if the core of the Earth cools, it will solidify. At the moment, we have a molten core which is producing a dynamo effect of a magnetic field. If the Earth's core solidifies, we lose that dynamo and we lose the magnetic field, which means we lose the protection from cosmic radiation. Okay, we lose the radiation protection from the sun, but maybe that's not quite so severe now that the sun is only a white dwarf. But we do lose that protection of cosmic radiation. It is hypothesized that this is what happened to Mars. Mars is a smaller planet. It would have had a liquid core originally because of radioactive elements at the core. That would have given Mars a magnetic field, but Mars is smaller. It cooled off faster. It solidified its core sooner than Earth's did. And as a consequence, Mars lost its magnetic field a long time ago. Mars lost its magnetic field. It was exposed to radiation from the sun and the rest of the cosmos, and it lost its atmosphere as a consequence. So Mars is the way it is simply because it's a smaller planet than the Earth, and it lost its magnetic field a long time ago. We will eventually lose our magnetic field, but only after the sun has had its last swan song. If that wasn't enough, the sun has gone through a red giant phase. The Earth has lost its magnetic field. Surely nothing else can happen. Andromeda is just waiting to crash into the Milky Way on a similar sort of timescale. A few billion years, the Andromeda galaxy, it can be calculated what the relative motions are. The gravitational pull of the Milky Way and Andromeda mean that the Andromeda galaxy is going to come in our direction, and after some 3.7 billion years into the future, it's going to be a huge object in our sky. Those of you who like astrophotography, get your cameras out, because this is going to be spectacular. At the moment, it's 2.5 million light years away, but eventually it's going to get closer and closer and closer, and basically the two galaxies are going to pass through each other. It's unlikely that any given star in one galaxy is going to collide with any given star in another galaxy. They're probably going to pass through each other. The gas and the dust is going to interact, and there's going to be an enormous new phase of stellar formation. Individual stars are going to survive. Lots of new stars are going to end up being generated by the tidal effects of one galaxy passing through another. They're going to pass through each other and come out the other side, and then eventually they're going to oscillate a few times before eventually settling down to a new mega galaxy, which is essentially everything that was in the two separate galaxies. By 5 billion years into the future, we're going to have probably an elliptical galaxy rather than two spiral-armed galaxies, and we're going to have to think of a new name for it. Milky Way and Andromeda, so the new one is going to be called Milkdromeda or something, but we've got 5 billion years to come up with a name, so that's not really a problem. Eventually, the black holes at the center of the Milky Way and the center of the Andromeda galaxy, eventually those two black holes are going to merge as well. But this is not necessarily a problem for us. The sun is unlikely to be hit by another star. Even if the sun gets ripped out of the Milky Way, it'll simply take its planets with it. The timescales are so slow that it's not like it gets ripped out overnight. It'll take millions, if not 500 million years for the interaction of the two galaxies to happen. And if the sun gets pulled away, the planets will simply go with it. So that doesn't mean necessarily a problem for the Earth just because we happen to be colliding with Andromeda. It sounds apocalyptic, but actually it isn't. We're now 10 to the 11. We are now 100 billion years into the future. This looks like a Photoshop of the Earth and the Moon, or possibly the Earth and a digestive biscuit. But no, it's an actual picture from the Deep Space Climate Observatory of what the Earth and the Moon look like from a distance. So that is the fully illuminated far side of the moon and obviously a sort of full Earth. This is here because at this point it has been calculated 1 day will be the same as 1 month. In other words, the length of time it takes the Earth to rotate once on its axis will be the same as the length of time it takes the moon to go around the Earth. They will be in lockstep. The Earth will be tidally locked to the moon, so one side of the Earth will always face the moon. We know that one side of the moon always faces the Earth. That's been the situation for billions of years. We know that's been ever since probably back to the formation of the moon itself. We know the moon has been tidally locked. But eventually the Earth is going to be tidally locked, so they will simply be facing each other and rotating as a pair, in much the same way that Pluto and Charon do at the moment. So if you think about it, if any survivors of the Earth are sitting on a continent, one side of the Earth will always see the moon in the sky. It won't rise, it won't set, it'll always be at a certain point in the sky. And half of the Earth will never see the moon. It will never rise above their horizon. So that's just a consequence of the way tidal locking will work. It's taken a while for the moon to slow down the Earth. We've seen it in terms of how often we need to introduce leap seconds. That's the ultimate conclusion, that basically they will be locked together. We are now at 10 to the 12 years into the future. We're now at 1 trillion years. All the galaxies in the local group are going to end up merging. There's the Milky Way right at the center there. The Milky Way is surrounded by quite a number of small galaxies. I can't remember how many objects there are in the local group. There might be a few hundred or so. The Milky Way is surrounded by lots of dwarf galaxies. And of course, also in the local group, we have M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy. So not only will the Andromeda Galaxy collide with the Milky Way, essentially everything we see in this map, everything within a few million light years, will end up being absorbed into one mega galaxy. The Milky Way will hoover up all the smaller galaxies, will collide with Andromeda, eventually it will collide with the Triangulum Galaxy as well, and you'll end up with one, probably not spiral, one huge elliptical galaxy. What will happen to galaxies beyond our local group? Well, as some of you will have heard from last week, according to the talk on ancient light, we know that it's possible to image and observe galaxies that are actually receding from us faster than the speed of light. The universe is expanding at such a rate. If you go to greater distance, the recession velocity is greater. That ratio is called the Hubble constant. If you're twice as far away, you're receding twice as fast. So there are quite a few galaxies out there receding from us substantially faster than the speed of light. It is definitely possible to image some of those. I've done it myself. And we know that the Hubble deep field on the right-hand side there, a lot of those galaxies that you can see in the Hubble deep field, a lot of those galaxies are receding from us faster than the speed of light. Only the very closest ones will actually be receding from us at lower velocities. But there will come a time, on a time scale of 10 to the 12 or so, when the expansion of the universe, as it will continue for another trillion years, we assume, if the expansion of the universe continues, there will come a time when the galaxies beyond our own galaxy are receding from us so fast we will not be able to image them. In other words, we have a Hubble telescope that can look out into the universe and see trillions of galaxies, or at least a small section of the universe from which we deduce there are trillions of galaxies out there. But it's sobering to realize that if a civilization comes to be in, let's say, 10 to the 12 years into the future, even if they build themselves a Hubble Space Telescope, if they look out into the universe and try and do the same thing, they will actually see nothing beyond their own galaxy. They will see stars. There were 2 stars in the Milky Way that came into the Hubble deep field there. A civilization in the future that tries to do the same thing will point their telescope beyond their own galaxy and they will see nothing, because the universe is simply expanding too fast for them to catch the light from these distant objects. A civilization that comes to be in a trillion years' time will come to the conclusion that the entire universe is just their own galaxy, because they will not have any clue whatsoever that there is anything beyond that. It's nothing to do with their technology, it's the limitation of the speed of light. We are at 10 to the 12 years. We're on the right-hand side of this scale, not quite at the end yet, but we're at the right-hand end of the scale. And I remind you that in the beginning of everything, we said it took 3 minutes to make all of the hydrogen in the universe. After 1 trillion years or so, it's starting to run out. There's not an infinite supply. The Big Bang made a certain amount of hydrogen in any given volume. It took 3 minutes to make it all, and ever since then, stars have been fusing hydrogen into helium, into carbon, into nitrogen, oxygen, etc. But after 1 trillion years, there's no more nitrogen, so no new stars. Well, maybe, maybe not. Some people have hypothesized, this is a little bit out there, but some people have said, well, maybe you can start with something other than hydrogen. If the hydrogen's gone, can you start making stars out of heavy stuff? Can you start making stars out of carbon or nickel or something else? Some people have said, well, according to my calculations, it might be possible to start fusion reactions with heavy elements even if the surface temperature is quite low. Now, not everybody agrees with this, but some people have said you can, in principle, make a star with fusion reactions at the core, but the surface temperature could be substantially lower than, for instance, the temperature of a red giant. A red giant has a surface temperature of about 3,000 Kelvin. Maybe it could be 10 times colder. If it was 10 times colder, the surface temperature would be barely a few hundred Kelvin. It might be possible to make a star with fusion at the core, but ice in the atmosphere. Frozen stars. Now, Disney have got their own version of frozen stars. If that's the picture you've got in your head, that's all wrong. So just let it go, because what I'm talking about, thank you, what I'm talking about is fusion reactions in the core, but ice in the surface. By no means everybody agrees on this, but it's an intriguing idea. But before we go any further beyond the end of 10 to the 12, because yes, we're not done yet. If we want to go any further, we've got to agree, or at least have a think about what's happening to the universe. If we think of the relative size of the universe, just how big it is compared to how big it is now, as a function of time, there's now at a size of 1, and the various colored lines indicate how the universe might change its size as a function of time, depending on the different colors tell us how much stuff there is in the universe. So the universe used to be a lot smaller, and hence the Big Bang occurred at 0 size at some time in the past, which depends on which model we choose. And if we say, well, let's take the orange line, if there was lots of mass in the universe, far more than we can actually see, way, 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 way more than we can actually see, then if there's enough mass in the universe, gravity will win and start to pull the universe back together again. So the size of the universe will increase for a while, but then it will start to decrease and end up going back to 0 in a big crunch, a so-called closed universe. So that, when I was young, was a definite possibility. But we now think that that's not the way the universe is. That's not the universe in which we live. We think it's not the orange one. We think we're actually on the red line rather than anything else. It's, for a while it was thought maybe we're on the green line, which will increase and increase and increase and slowly slow off. But we think we're on the red line, which means not only is it increasing as a function of time, but the gradient is getting larger and larger as well. Not only is it expanding, the expansion is accelerating via a process which we don't understand. We give it the name dark energy, and we pretend we understand it, but we don't. So we think that's the universe we're on. There's no hint of it actually wanting to turn around into a big crunch. So as far as we can tell, the universe is going to go on forever, and there's no obvious way that it will directly end. So in order to make any headway so as not to be here until midnight, we're going to have to change gears. So instead of going up by a factor of 10 in each box, we're now going up by a factor of 1,000,000 with each box. Otherwise, we'd be here literally all night. So we've got numbers like 10 to the 30, which is a zillion. Oh, I don't know. Is it a gazillion? I don't know how big. The labeling of these things gets ridiculous. So we're just going to rely on 10 to the really big number. And that number is going to continue getting larger and larger above 12. So where did we leave things before we took this aside and said the universe is going to go on forever? We said all the hydrogen was made in 3 minutes. The hydrogen is running out. Stars can live for a long time. Stars can live for trillions of years, but they don't live forever. So what does that mean? There will come a time when there are no more stars. It'll take quite a while, but the last star will go out. The universe will continue despite the fact that there are no stars shining anymore. When the age of starlight comes to an end, these objects that are no longer shining through thermonuclear fusion will continue to move the way they were moving in the first place. They will still continue orbiting their galaxies. These dead stars will be basically zombies: white dwarfs, neutron stars, and black holes. White dwarfs, we said, like our sun, basically just a lump of carbon. Neutron stars, a collection of neutrons. Black holes, who knows what they are, other than they are very compact, producing very strong gravity in a very small area. There are no nuclear reactions keeping white dwarfs hot. They are white, but they're not shining in the sense that they are shining like stars at the moment, burning nuclear fuel, fusing hydrogen or helium or heavier elements to make energy. They are just simply hot cinders. They just happen to be a lump of coal, which is quite hot, but it will cool off. So white dwarfs will eventually cool down and become black dwarfs. It'll take a little while, but remember, we are talking a long, 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 long time here. And it's very difficult to see what that picture is. If I make it a little bit brighter, it probably doesn't help. It's just a lump of carbon. That's all a white dwarf basically is. And it starts off bright just because it's hot, and eventually it will cool down. Any stars that aren't ejected from the Milky Way, it's thought that some stars will be ejected from the Milky Way, but those that aren't will end up getting hoovered up by the supermassive black hole, hereafter just SMBH. The supermassive black hole at the center of what we believe is every galaxy will simply hoover up any stars that are left. A recent observation of a particular galaxy, going by the wonderful name of NGC 1097, the magnetic field at the center of this galaxy has been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy, the infrared telescope sitting in the back of a jumbo jet. Unfortunately, recently decommissioned. It was just a little too expensive to keep running. But this particular observation was made, and they mapped out the magnetic fields close to the center of this galaxy. And it's thought that when a galaxy comes towards the end of its life, when the stars have all died, the matter that's left will end up getting funneled by these magnetic fields, and that's the mechanism by which supermassive black holes basically hoover up anything that's left. Matter simply follows the magnetic field lines until it ends up in the supermassive black hole, which we can't see right in the center of that particular galaxy. And as far as we can tell, we believe the mechanism would be the same in any other galaxy. What's happened to all the atoms in the universe? Well, atoms are positively charged nuclei made of protons and neutral neutrons, and we have negatively charged electrons buzzing around them. The protons are responsible for giving the nucleus of an atom its charge, but we don't know if protons last forever. Protons might decay, in which case, if they do, every atom in the universe will fall to pieces. It's not going to happen on timescales less than this. If atoms do fall apart, They will happen on timescales probably greater than 10 to the 36 years. But we don't even know if it will happen at all. People doing experiments at the moment cannot tell whether or not protons will decay ultimately. So it's not going to happen for a while. If we assume that it doesn't happen for a while, then atoms will continue to exist for quite some time, but even the only atoms that exist will be in the centers of black dwarfs. There are no atoms in neutron stars. There are no atoms in black holes. Eventually, black dwarfs will evaporate, and there will be no atoms left in the universe. There will still be matter, but no atoms. We know that when galaxies merge, the supermassive black holes at the center of those galaxies end up merging. So perhaps we'll have black holes that aren't millions of solar masses, or even billions of solar masses. Perhaps if we wait long enough, we will find that we get supermassive black holes of trillions of supermasses, trillions of solar masses, as all these black holes eventually merge together. But even black holes are not eternal. They do not last forever. They evaporate as long as you wait for a really, really, really long time. Note where we are. 10 to the power 66, silly number of years into the future. Why do black holes evaporate? Well, a little aside on what we believe is going on with quantum theory. Quantum theory allows energy to be borrowed from nothing to allow you to make particles and antiparticles, matter and antimatter. You can borrow energy from the bank of nothing. You can make matter and antimatter. They annihilate, and you get the energy back, and you pay off the loan. Energy produces stuff, ends up annihilating, and you get energy back again. As far as we can tell, that happens all the time. And it doesn't violate any laws of physics. As long as you pay back the loan quickly enough, you can borrow, make matter and antimatter, and pay back the loan afterwards. How's that relevant to black holes? What happens if you borrow and make matter and antimatter, but you do that right next door to a black hole? There's the event horizon of a black hole. What if you borrow and make matter and antimatter, but one of them has gone into the black hole and the other one hasn't? You now can't have the matter annihilate with the antimatter because one has disappeared from the universe into a black hole and the other one is now floating around. It looks like the black hole has spat something out. And when you work out the maths of what's happening to the matter, what's happening to the energy, you get effectively a net radiation from the black hole. Stephen Hawking first proposed this. It's called Hawking radiation. We haven't actually seen Hawking radiation, but it is widely believed that that is going to limit the lifetime of black holes. The radiation increases with decreasing mass, so the radiation for large objects is very small, but as the object shrinks due to this radiation, it'll radiate faster and faster and faster and faster. So large objects will radiate, and we can't see them radiating because there's just too little of that radiation. But as they start to evaporate, the radiation levels will rise until it disappears in a flash of radiation. Even supermassive black holes, even the really big ones, even the ones that are trillions of solar masses, even they will evaporate as long as you have the patience to wait for perhaps trillions of times longer than it would take for a solar mass black hole to disappear through evaporation. So have we reached the end? Well, we've reached as far as I want to go with that timeline. It's been estimated that if you take 10 to the power 100, which is a Google, no, not that one, that's a misspelling of Google. Google with an OL is 10 to the power 100. Google with an LE is just a misspelling of Google. So 10 to the power 100 is a Google. And it's been estimated that after a Google years, the last black hole will have evaporated, as best we can calculate. That means there's nothing left. After that, nothing happens. And so the concept of time starts to become absolutely and totally meaningless. We think about time in terms of the motion of things, whether it be a sundial and the motion of the sun, or whether it means the phases of the moon and the way the moon changes. We measure time by looking at things changing, a candle burning down, water flowing over a wheel, whatever. If there's nothing there and nothing changes, then the concept of time just goes completely out of the window. So strictly speaking, 10 to the 100 isn't eternity, but it's as good as far as the future of the universe is concerned. I don't often do this, but just to remind you how ridiculous that number is, let's write it out in full. So there we have it, 10,000 million. Oh, you do it yourself. Yes, okay. It's a ridiculous number, even ridiculous compared to the large numbers. If you thought billions and trillions and quadrillions were large, they're nothing compared to a Google. And as far as we can tell, the Google is where the universe stops being interesting, because nothing happens from this point onwards. So it's not strictly speaking eternity, but as Woolly Allen once said, eternity is a very long time, especially towards the end. But I find that the XKCD cartoons are quite insightful, and they've got a little quip as to how you can relate mankind to the age of the universe. A human, they say, is simply a system for converting dust billions of years ago into dust billions of years from now via a very roundabout process, which involves checking email a lot. So that puts humans in their place, doesn't it? So I don't want you to leave totally depressed about the universe ending, so I'll give you a two-minute epilogue. We live in a golden age. The sun is middle-aged, it's well-behaved, it's stable. And the moon is at the right distance to stabilize the Earth's axis and stabilize the Earth's seasons. As a bonus, it also gives us the spectacle of a total eclipse of the sun. And we are able to explore and discover and understand the universe by building probes through which we can visit our nearest neighbors, or we can build telescopes using which we can see trillions of galaxies, billions of light years distant. But we couldn't have done this in the early universe. Mankind couldn't have arisen in the very early universe because we needed lots of sequential generations of stars. We needed lots of stars to convert hydrogen into helium and then explode. And we needed stars to convert helium into carbon and nitrogen and oxygen and phosphorus and calcium and iron. Otherwise, we couldn't be who we are. So mankind could not have existed in the early universe. And I've just shown you that the far future is really dark and really boring. So you could say the best time to exist is now. Thank you for listening.
Thank you.